here we have a vector valued function that we want to find the derivative at a point. So remember in Calc 1, when we had a curve, if we were finding the derivative at this point, we looked at secant lines as our point got closer and closer to the point we wanted. And we looked at the limit as the change in x goes to 0 of the change in y over the change in x is equal to the limit as change in x goes to 0 of f of x plus the change in x minus f of x all over the change in x. So we're going to do something similar with our vector valued function. So here we have the case where we can draw, let's say we want to find derivative at this point. So what we can do is we can find a vector close to it, and then we can find the vector that connects them. Then we're going to get a little bit closer. We find the vector that connects them, and closer still, the vector that connects them. So eventually we're going to get our derivative, much like in the case of our secant lines. So with our vector valued functions, our derivative r prime of t is the limit as the change in t goes to 0. So that is, t is getting, my t value is getting closer and closer to this green one, of the change in r over the change in t, which is equal to the limit as change in t goes to 0 of r of t plus the change in t minus r of t all over the change in t. So this is our formal definition of the derivative, much like we had the limit definition in Calc 1. But just like in Calc 1, we had rules to simplify things. We also do in vector valued functions. So given a vector valued function, r of t equals f of t, g of t, h of t, where f, g, and h are defined on the interval a, b. The derivative of r of t exists and is given by r prime of t equals the vector f prime of t, g prime of t, h prime of t on the interval a, b. If the derivative does not equal 0, then the derivative is a tangent vector to r of t. So let's try an example. So here we have sine of t, t squared cosine of t, and this is actually this function that we graphed. So if we want to find the derivative, we take the derivative of f. So f prime of t is cosine of t. We find the derivative of g of t, and that is 2t. Find the derivative of h of t, that is negative sine of t. So our derivative, r prime of t, is the vector cosine of t, 2t, negative sine of t. And so we note that all of these, three of these functions have domain of all real numbers. So this is differentiable for all t. Now, let's have you try one. So go ahead and try r of t equals t squared square root of t, and try and find the derivative. So the derivative of t squared is 2t. Derivative of square root of t is 1/2 t to the negative 1/2. Derivative of t is 1. So this is true for what? For if we're in the interval 0 to infinity, because we can't have anything less than 0 under the square root. So we're differentiable from 0 to infinity. So here we have that function that we just took the derivative of. Here we see in the red is the derivative function that we just found. And in the black is our original function that we took the derivative of. So we're trying to find the derivative at this point here, and the corresponding value on the derivative function occurs here. So we find that vector, then we drew in the parallel line, and the portion of this line that has the same length as this vector here will be our tangent vector. So here we see our tangent vector, and we would just need to cut this line off at the length of this vector here. So now let's look at the vector r of t equals t cubed t to the 4th t squared. So when we find our derivative, we get 3t squared, 4t cubed, and 2t. So what happens when we graph this? And we notice that at the point 0, 0, 0, we have a point that we call a cusp. So with any function that contains a point 0, 0, 0, you will have a cusp, and there is no derivative at that point. Another thing to notice is that curves have orientation. What that means is that when we plot this curve, and we start from negative numbers and move towards positive numbers, this is the direction in which our curve is building. So we can think of this curve as having little arrows that point us this way. So our derivative will point in the same direction as the orientation of our curve.